Today, we're going way, way back. We're talking 13.8 billion years to tackle the biggest question there is: where did all of this come from? It's a story about a brilliant theory, the huge holes that appeared in it, and a single radical idea that came along and fixed it all in the blink of an eye.
I mean, really, this is the ultimate question, isn't it? How did our incredible, sprawling universe just appear? For most of human history, that was a question for philosophers and poets. But today, science has a pretty mind-blowing answer.
So, to even begin to tell our cosmic origin story, we have to start with the big one, the theory that completely changed how we see everything: the Big Bang.
Now, when you hear Big Bang, you're probably picturing a huge explosion, right? Like a cosmic firework. But you gotta get that image out of your head. The Big Bang wasn't an explosion in space. It was the moment space itself started expanding, from a point smaller, hotter, and denser than you can possibly imagine.
And listen, an idea this big doesn't just appear out of nowhere. It started back in the 1920s. First, a physicist and priest named George Lemaitre had this wild idea that the universe was getting bigger. Then, a couple years later, Edwin Hubble looked through his telescope and actually saw it happening. He saw that all the distant galaxies were flying away from us. That led Lemaitre to a logical conclusion: if you run the movie of the universe in reverse, everything must have started from a single, tiny point, a primordial atom.
I'm going to say it one more time because this is the single most important part to get right. It wasn't a bomb going off in a pre-existing empty room. It was the room itself, the very fabric of space and time, stretching out in all directions, carrying everything with it. That's the Big Bang.
Okay, so that's a pretty epic story, but it's also a massive claim. So how in the world are scientists so sure about it? Well, it turns out the whole theory is propped up by 4 rock-solid pillars of evidence. First, you've got the expansion itself, the thing Hubble saw. We can literally watch the universe getting bigger. Second, there's this thing called the cosmic microwave background. It's like a faint leftover heat from that initial fireball, and it's everywhere. Third, the theory's math perfectly predicts how much of the light elements, like hydrogen and helium, should exist, and it nails it. And finally, it gives us the blueprint for how all that stuff eventually clumped together to form galaxies and, well, us.
And here's the coolest part. That leftover heat isn't some abstract thing. It is literally all around you right now. In fact, if you're old enough to remember those old TVs with the antennas, about 1% of that fuzzy static, that snow between channels, that was the echo of the creation of the universe. Wild, right?
So, the Big Bang Theory is looking pretty good. Case closed, right? Well, not quite. See, the closer scientists looked, the more they found these really deep, really nagging problems. Little loose threads that threaten to unravel the whole thing.
Okay, puzzle number 1, the horizon problem. When we look at that afterglow from the Big Bang, it's almost the exact same temperature everywhere we look. But here's the problem. Parts of the universe on opposite sides of the sky are so far apart that there hasn't been enough time in 13.8 billion years for heat to travel from one side to the other. They've never been in contact, so how did they agree to be the same temperature? It just shouldn't be possible.
Then you've got the flatness problem. Now, stay with me here. The geometry of space-time can be curved, kind of like the surface of a ball, but our measurements show that it's almost perfectly flat. The thing is, the physics says that if it started with even a tiny, microscopic curve, after billions of years of expansion, that curve should be huge by now. To be this flat today, it had to start out flat to an insane degree of precision. It's like balancing a pencil on its tip for 14 billion years. Why?
And the last big headache, the monopole problem. You know how every magnet has a north pole and a south pole? You can't have one without the other? Well, the theories about the super hot early universe predict that exotic particles that are only a north pole or only a south pole, magnetic monopoles, should have been created in massive numbers. But we've looked everywhere, and we've never, ever found one. Not a single one. So where did they all go? So these 3 puzzles were giving cosmologists a serious crisis. The best theory of the universe had these giant holes in it. And then, in 1979, a physicist named Alan Guth came up with a jaw-droppingly bold solution. He called it cosmic inflation.
The idea goes like this. What if, in the very first, tiniest fraction of a second of existence, the universe went through a short, violent, absolutely insane burst of expansion? We're talking about a period of time so short that it makes a nanosecond look like an eternity.
And how fast was this burst? Get this. In that sliver of a moment, the universe expanded by a factor of at least 10 to the power of 26. That's a 1 with 26 zeros after it. To put that in perspective, something smaller than a single atom would have ballooned to bigger than a galaxy in less than the blink of an eye.
So this isn't the gentle, steady expansion that's happening now. This was a hyperdrive moment. It happened so fast, the universe supercooled, and then when inflation stopped, all that energy reheated it in a flash. And here's the kicker. This incredible stretching process took tiny, microscopic quantum fluctuations and blew them up to cosmic size. Those tiny jitters became the seeds of everything we see today.
And this is where it all clicks together so beautifully. This one idea solves all three problems at once. The horizon problem? No problem. Before inflation, the entire observable universe was a tiny, connected patch where everything was the same temperature. Inflation just stretched it out. The flatness problem? Imagine you're an ant on a giant inflated balloon. The surface looks perfectly flat to you, right? Inflation did that to space-time. And the monopole problem? They might have been created, but inflation stretched the universe so much that they were diluted across a vast space, making it statistically impossible for us to ever find one.
So inflation is amazing. It plugs all the holes in the Big Bang. But it also leads us to one of the most profound and frankly weirdest ideas in all of physics.
Alan Guth himself called inflation the ultimate free lunch. But what does that even mean? We're always told there's no such thing as a free lunch. You can't just get an entire universe with all its stars and galaxies and energy for free, can you?
Well, the secret is that the total energy of the universe might actually be zero. It's a shocking idea. See, all the stuff, matter, light, everything, has positive energy. But gravity has negative energy. And it just might be that for every bit of positive energy created, an equal amount of negative energy was created in the form of gravity. They cancel out perfectly. And if the total cost is zero, well, then it doesn't take any energy to create a universe. It could literally just pop into existence from nothing. So let's just wrap our heads around this. The Big Bang Theory tells us our universe has been expanding and cooling for 13.8 billion years. It had some serious problems, but this incredible idea of cosmic inflation, a brief, violent burst of growth at the very start, solves them all perfectly. And maybe the most amazing part is that it suggests that every galaxy, every star, every single thing we see started as a random, microscopic quantum jitter in that first moment.
And that leaves us with one final awe-inspiring question. If the laws of physics allow a universe to spring into existence from nothing, who's to say it only happened once? If inflation can create our universe, maybe it's happening all the time, constantly budding off new universes in a vast cosmic foam. It's a thought that really pushes the boundaries of what we can know and even what we can imagine.